something that probably is still relevant to your assignment that's due tonight. So if you have some last minute revelations, you probably can hopefully take care of those things before it's due. All right, I think you have a second part to this assignment, and then one more written assignment that's coming, and that's it. So you have one more programming and one more written assignment. And that's the end of your assignments, right? So and then we go for the final exam. Okay. So the topics that we want to discuss today are two things, and then I will discuss them in the. So, for example, we're going to be discussing this week searching and sorting. Okay, searching and sorting. All right? And when we discuss these things, we will not only just discuss how to search an array of integers, but also how to search an array of objects, like maybe songs, right, or the robots. What's wrong with this? No, just put the battery. Can you guys hear me in the back? Yes. You're okay, all right. So I'll work it out. Okay, so searching. There are two things that are important: linear search, one algorithm, a simple one, and then there's a bit of a complicated algorithm called binary search. Although the idea is really, really simple there. Okay? When it comes to sorting, we'll talk about two things. One is called selection sort, and the other one is called insertion sort. So you probably have to pay attention to the whole discussion about searching and sorting, because there could be questions in the written assignment that's coming up about the complexity of these things. You know, what's the best case, what's the worst case, how can you count the operations, things like that. Okay? Now, when you do search, okay, there's one thing that's really important to us, right? When you do search, you have to know, because you're searching for a target. So we ask the question, is something in the list is equal to something the target, okay? But this equals has a lot of different meanings, right? Because when you talk about equals, right, if you have like int and double and even Boolean, okay, for equals we can use that. We compare two things, all right? But when it comes to objects, okay, when it comes to objects, this doesn't work, right? So you need to have some method called equals that's defined. Now, this already exists in the API methods. Like, for example, if S1 is a string and S2 is a string, you can ask the question, is S1 equals to S2? Right? That should return a true or false answer. That's for the strings, right? But if you have two songs, okay, so if you have song 1, is that equals to song 2? It's another question, right? So this equals doesn't exist, and you have to write it. Okay, it exists for the if you want to know whether two songs are equals or two robots are the same, you have to write it. That's why. Okay. All right. So equals is the main operation we need for the searching. That's it. When it comes to sorting, we need an operation called compare to. Okay, we need an operation called compare to because if you're going to sort something, then you have to know the order. So you have to know if you're given, say that you've given two objects, A compared to B. Right? Is it greater than 0, less than 0, or equal to 0? So the equal to 0 is more like the equals, right? It's the same thing as equals. But it could be greater, it could be less, so that we can order things in a list of things when you're sorting. Okay? So the first thing I want to go through is the this idea of, so how do you write equals for something like Carol the robot? Okay, so let's take a look at that. See, it's coming up here. Okay. So what we're going to do is we're going to sort of write a method in the Carol the robot class. Okay, so let me just delete all that stuff. Okay. So what I like to do is it's a sort of a class we developed earlier in the course. What it does is Carol the robot create robots. Okay, so they have attributes, just like your song class, right? So now I want to write a method called equals for the Carol the robot. Okay? The way I will define equals, it says something like this. I say two robots are equal if their IDs are the same. All right? Okay, so we know that there's a attribute here in the robot class called robot ID. Keep the noise down a little bit, like I can hear something from the middle. Okay, keep the noise down so I'm not distracted. Right? So we want to write equals, okay? But the equals signature is given like this. It is an object that's given. In other words, if you're calling equals, you say, I'm a robot, I want to know whether I'm equal to some other robot, right? So this other is the robot that you're going to try to compare yourself to. Right, there are a few things you have to do first. First of all, you have to make sure that the other is not equal to null. Because that other could be a null object. If it's null, I cannot compare, because it doesn't exist. Right? So in that case, I will say, I will return false. Because I don't know how to compare null objects to myself. Right? The second thing you have to check is whether this other object is actually a Carol the robot. Okay, for that, there's a method called, so if I take other, and there's a method called instance of. Right? Is that right? Other instance of? The lowercase of? That's why I didn't count. Right, thank you. Okay, so instance of is an operator. It says, is this an instance of Carol the robot? Okay? So we're asking that question, is that true or false? In other words, if you're going to compare two things, they better be the same thing, right? We only can compare the apples and oranges because they have different attributes. Right? Here I'm going to say something like this. If it's not, okay, so if it's not the this, return false. All right, so that's the second check that we have to do to make sure that it's a Carol the robot object. Okay, so if I get through that, then I know it's a Carol the robot, but I'm not still done. Because what I want is, because the object is still an other. Okay, so what I need to do is, I take other, okay, I will typecast that to Carol the robot. And then I will assign it to a new object, which is of the type Carol the robot, new robot, like we can call it new robot or something, right? Or the other robot is better, right? So let's give it a different name than the other. The other robot is equal to this. What I just did is called casting. Okay, without casting, you cannot really call the methods of an object. You have to cast it. Okay, so what I did was I got the other robot, I checked to see if it's an instance of a Carol the robot, and then I'll cast it to make it the other robot. Now I'm in business. I can now compare two things. I want to know whether they're equal. So I only have to do a simple test here. For you, I think you have to do a bit more, but it's just adding more questions. So if I just say, if this dot robot ID, okay, so let's take robot ID, is equal to, we know that's going to be an integer, so I can just use equals, okay, is equal to the other robot, right, dot robot ID, okay, return true, right? So this is saying if two robots are the same ID, then they are the same robot. Okay? Else, return false. So this is a simplified sort of version of the song equals right method you have to write, but it's very similar. You just have to do a little bit more checking for the song equals. Okay? Any questions? All right, that's it. And how do we check this? You have to test it, right? So if I want to test the equals method, so let me save this, and I'll show you some code that will test it. If you didn't write it down, you just wait a little bit. Oops. Oh, yes. Okay, I'll test it here. I will test it in another place. Okay, so here's how I'm going to test it, okay? So I wrote the equals method. So let me create a robot. Okay, so this is creating robot 1, robot 2, robot 3, robot 4. Okay? Now, according to my definition, which robots are equal? Robot 2 and 4, right? So let me just test it. Okay, so notice that this equals now is the one I just defined. It's in the robot class. I'm calling it from another class, not search or so. Right? So this is supposed to return true. Okay? So I'm checking my robot method. So let me just go here and, oops, I have an error here. There's that error line. So the Cal robot line, what, 118? Cal robot line 118. Okay, is that, oh, I guess I didn't complete these things. So let's say return 0 here, because it's supposed to return something. Anything else I need to worry about? So it's complaining that because I didn't complete that. Right? So go back to searching.
Just the arrow next to the bracket, you just condensed the
Oh, it's supposed to open, right, okay, good. So, all right, so let's test that. Return statement, 118. Maybe I didn't save it. We go to Cal Robot and save it. Save it, go back to searching. Okay, good. Now let me just run it. So it says true. Right, so it's supposed to be true if robot 2 is equal to robot 4. But what if I change it? Say I ask the question, is a robot 1 equals to robot 2? So let's try that. Okay, so in that case, the answer is false. All right, so yeah, so you saw that. So the way I did this is to write a method called equals to do this, right? Now what I'm going to do is I'm going to use this equals method to search for a robot. Okay, so suppose I'm searching for an array of robots and I'm looking for a specific robot. Okay, so, and this means I have to write a search method. Okay, so I'm going to write a search method, which is, I'm going to write what's called the linear search, which we have already looked at, so I'm going to go to searching and write this method. Okay, so let's do this one here. So this is the linear search. As you know, we have talked about this before. The idea of the linear search is that given an array of anything, you just start from 0, 1, 2, up to the end of the array. You compare to see if they are equal to the target limit, and then you're done. Okay? Now, there are a few checks I have to do. When I write this, notice that this method takes an array of objects, array of Carol robots, and a target object. Okay? So I want to make sure that the object is a real object, right? It's a robot because I can't compare otherwise. So I'll do one test like this here. I'll say something like this. If the object is equal to null, okay, or, right, if the object is not an instance, so let's say it's not, so if this object, my mouse jump around, object, instance of, okay, Carol the robot. Okay, so what this says is that if the object is null, which means I don't want to do anything, or it's not a Carol the robot, then I want to return false. Okay? Otherwise, object is a robot, right? So this means that I want to typecast next. So I'm going to say something like this. Carol the robot, other robot, is equal to Carol the robot, and other. So this is really important, that typecasting is important, because if I don't typecast, I cannot really do anything with the methods. Okay? And then what I'm going to do is I'm going to run the regular linear search algorithm, which is not difficult to understand, because all you do is you run a loop through the whole thing, I less than a.len, I plus plus. Okay, so I would say something like this. If, right, I want to check whether two robots are the same by looking at their, using equals. Okay, so I will say this dot equals, right, and the other robot, okay, return true. That's like saying, I found an element, is y equals target. Instead of saying is y equals target, now I'm saying, I'm using equals method because it's how we are supposed to compare robots.
Professor,
Okay?
you're using target, not object or object.
Yeah. Other isn't a parameter.
Other is,
Target's what you're trying to.
oh, yeah,
Yeah.
that's right.
I just
So,
think-
what am I doing here?
You wrote object and other.
You're casting it to other.
Oh,
but
it's
that's
not
a
other, it
parameter.
should be target.
And then the condition.
Yeah. So this should be target, right? All right, what else?
If statement.
If statement? Okay, so if,
Above, you're setting object equal, you're checking if object is not, should be a target.
thank you. Target equals null or target is, okay, so we have to pay attention to these things. Compiler would recognize this and you would immediately know this is false. So now I'm good, right? So I'm saying, I'll go through the loop, and if I find some robot, okay, actually this is not right, right? It's not this. What am I comparing? So object at the ith place, right? So you have to say A bracket I. All right? It's like saying AI is equal to target. So now we are saying AI is a robot object. Okay, I'm going to see if it's equal to the other robot.
Oh, yeah.
Okay, all good? Do you see any problems here? Okay. So if I don't return true from this loop, right, so that means I didn't find it, so therefore it should be false. Okay? So now let's see how we can test this code. All right? So I'm going to test the linear search code by creating an array of robots and a target robot and see if it's going to work. Okay? So let's do this. I'm going to open up another robot. So now I have 5 robots. I'm going to give you this code, so don't worry about the topics. If you miss something, that's okay. Right? So then here's what I'm going to do next. I'm going to create an array of robots. Right? Pointer here. Okay. So here I'm creating an array of robots. In this case, I'm choosing the size to be 10. Okay? Now, you can assume that when you create an array of robots, everything is null. So just to be on the safe side, you could do that. Okay, so this will take the array. This array is not initialized. Okay, you can assume it's initialized to null, but you're not going to stick with Java forever. Right? If you go to other languages, the arrays are not initialized by default. So you have to do it manually. Okay, so I'm showing you a way to do it manually. So let's create the robots array, and let's initialize all the robots to null. Okay? And now let's do this. Let's randomly assign robots to places. So robot 1 will be on the position 1, position 0. Position 3 would be robot 2. Position 5 would be robot 3. Okay, and position 9 is going to be robot 4. Right, so what this does is that it fills the position 0, 3, 5, 9. Notice that I've created the object first, right? All right, so you still have null in places. So in this case, only the 0, 3. So if you actually look at the array of these robots, you're only going to see, okay, you're going to see a robot here, right? This is null. Where's the other one? 0, 1. The other one is 3, right? This is null. And there's a robot here, and so on. Okay? That's how the visualization of the robot should look like. Now let's do this. Let's linear search this array for robot 5. Robot 5 is not in the array. Okay? Let's linear search for the robot 5. So we wrote the method. So the method we pass the array of robots and the robot 5. Okay? What do you think the answer is going to be? True or false? False? All right, so let's do an experiment here. Oops. I got a problem. Right? The problem says null pointer exception. Okay, so now we have to think about why this happened. Okay? This happened for a really important reason that you will run into very soon. When we wrote the linear search, method. Okay? We gave an array, right? Where do you think the null point exception came from? The null point exception means that I'm giving a null object and I'm asking to use a method in the object. Obviously, if it's null, there's no method, right? So what should I do to fix the code now? Obviously, my linear search is bugged. Okay? So here, notice something here, right? Here I'm checking to see if AI is equal to this. But did I check whether AI is null or not? I didn't, right? Yeah.
If AI is null, is equal to null.
Okay. So we'll say something like this. If AI is not equal to null, and okay, so that's a fix. It's a fix because what I'm saying here is that if AI is null, don't do anything. Okay? The way the conditions are evaluated is that if this condition is false, if AI is null, it will never go here. Because if you have something and something, if the first one is false, the whole thing is false. So why even bother to evaluate the second one? Okay? So if AI is not null and AI, so if AI is not null, only you're going to go here. Okay, so that's a fix for making sure that there's no null point exceptions. Okay? Because what happened before was that some AIs are null, right? Remember my array? Some of them are null, some of them are not, and it ran into one of those null things. Okay? So let me go back and see if I can run this again. So here's my code. I will try to run it again. Okay. So it says that robot, so it says robot 5 is not in the array. But let me do something, okay? So let me say that I made the robot 5 12. Okay, so I gave the ID robot 5 the 12. Okay? Now what's the answer to this? Is it true or false? Well, according to this, robot 5 is not in the array, right? I only put 4 robots in the array. So robot 5 should not be in the array. Right? Okay, so let me do that. All right, so notice that now the robot 5 has the same ID as the robot 1. Okay, so if I run the code now, it says true. Right? Why is it saying true? Why is it saying that the robot 5 is in the array? Anyone? Yeah?
Because it's equal to robot 1.
That's right. Remember that our criteria for comparing robots was the ID. Right? So as long as the ID was the same, then we thought that the robot is in the array. So there's a problem, right? Okay? So it gives you the wrong impression that the robot is in the ID. Obviously, this is not a situation where you want to create duplicate IDs for robots, because it will create this sense that robots have to be uniquely different, right? Otherwise, they are the same robot, according to my equals definition, right? Okay. So that method is called linear search. Okay? Now we're going to talk about something called binary search. So now you saw how we can use so here's the idea of the binary search. Okay, so there's a very important assumption that the array is sorted. Because I cannot do binary search without assuming the array is sorted. All right? So what I like to do is how do I check whether an array is sorted? If I'm given an array, how do I check that array is sorted? Right, so you have an array. Right, so you're given a random array and you have no idea what's in the array. Right, maybe 5, 7, 8, and 10. I know by looking at it, it's sorted, but what's the algorithm for checking whether it's sorted? Yeah?
If a of I plus 1 is greater than a of I, we
Okay.
run a for loop.
That's right. So what we can do is something like this. We can say, let's look at two elements that are adjacent. Let's look at a's of I, and let's look at a's of I plus 1. Right? Let's look at two elements that are next to each other. Right? So if the array is sorted, if A is sorted, right, then we know this is true. A's of I is less than or equal to a's of I plus 1 for all I. I equals 0, I equals 1, I equals 2, up to whatever the length minus 1, right? Do you agree with that? If A is sorted, that condition must be true for every element. So if you're going to prove that it's not true, what are you going to look for? What's the logic here? Right? Because you want to prove something is true for a lot of things, right? What is the negation of that statement? The negation of that statement is what? That means if you negate for all, that means there exists one. Okay? The negation of for all is that there exists something. Right? So that means you have to show that there exists. Okay? There exists an AI. There exists I such that A's of I is greater than A's of I plus 1. So this means they are misplaced, right? Okay, so what I'm going to do is to program that to create a method which is going to be really useful for the binary search because we have to make sure it's going to work. Okay, so I'm going to write a method called isSorted. So the purpose of this method is to take an array and tell me whether it's sorted or not. Okay? That's what it's going to do. So before I do anything, I will say something like this. I will make sure that my array is not length 0. Okay? Because if you give me an empty array, there's nothing I can do. Right? So I will take care of that case. That's like an extreme case. And then to check this for every I, right? So I will go through this. So I write a loop. Okay, so I will write a loop like this for int I equals 0, I less than a dot length. Okay, I plus plus. And I'll say something like this. Now notice this is an array of integers, so I don't have to use equals or anything like that. I could use equals if I'm looking for an array of objects. Actually, I cannot use equals, so I have to use compare to. Right? So I can say something like this. If, how do I say this? If A is of I, right? I'm looking for the negation. I'm looking for, is this true? Right? So this means I should return false. So I'm looking for some I where that's true. That's going to be holding true. So I'm saying, okay, if you can find me one element, I, where A's of I is strictly greater than A's of I plus 1. That means the left guy is bigger than the right guy, then I will return false. This code is valid. Right? What's wrong with that code? Yeah.
As long as it's 1, you're going to get an out-of-bounds exception.
That's right. So notice that the last I is the length minus 1. If it's length minus 1, the I plus 1 would be length. Okay, there's no such thing called A of length, right? That's the array index out of bounds. Okay, therefore you only have to run this code. How do you fix it? Yeah, so just make it minus 1. Okay, so by doing that, you will avoid the array index out of bounds there. All right, so if I get out of that loop with no return false, if I didn't return false, that means I return true. This means I know the array is sorted. Okay, so let me test that. So always it's important to test the code, right? When you write the code, you want to show whether, like for example here, let's take this array. Okay, and let's call the method isSorted. Now you see that the way I call the method is sorted. Is this array sorted? Right? So I will test that, and let me just comment out these things so that you're not confused by the other output that we have. All right. So the only output I'm supposed to get is true. Right. So let me try that. Okay, so it says true, right? But does it really work? In order for me to know that, maybe I create an array that's not sorted, right? Everything is sorted except the last one, right? So now let me try this. Now it says false, right? So it's a good one, right? Because I can now use that to do the binary search. So before I do the binary search, I want to make sure it's sorted. You will see why it's necessary that it needs to be sorted. But let's talk about the binary search. So I think for the next assignment, you have to know how to trace some of these algorithms. So the whole idea of binary search is this. So given an array, let's say it's sorted, okay? Now, we're going to start with a left pointer and a right pointer. Okay, so that's the size of the array we are searching. Okay? And using these two things, we're going to compute the middle of the array. Okay, when I start, I'm going to start with L equals 0. Left is 0 because this is the 0 index. And right equals 5. OA dot length minus 1, right? If you have an array, that's what you would write. And I will use the formula to compute the mid. This is going to be the left plus right over 2. Okay, that's how I'm going to compute it. All right, let's see how we can trace this thing. Now, so let's say we have left, right, okay, and the mid, and A's of mid. So I'm going to trace this code to see what will happen. Okay, my target that I'm going to be looking for is maybe 2. Okay, my algorithm should work whether the target is not there or not there, okay? All right, so initially I'm going to start with, for this array, right? I'm going to start by saying left is 0, right is 5. What is mid? Mid is always this formula, okay? 0 plus 5 over 2. But we know when you do the integer division, 5 over 2 gives you what? 2, right? So mid, I'm going to get 2. Okay, and A's of mid would be this. 8. Okay, A's of mid is 8. Right? Now, here's the algorithm that I'm going to be using. If the target is greater than the A's of mid, okay? So suppose the target is on this side. It's bigger than that, right? So that means I only have to look here. So to do that, what I do is I will move this left pointer here. Okay? So I'll move the left pointer there and say, if this is true, then I will say left is going to be mid plus 1. Okay, remember that, see in this case, if I knew that my target is bigger than 8, I will have to look here, so my search space is, the left is going to be the mid, this is the mid plus 1. Okay? All right, now in the same argument, you can tell me if the target is less than A's of mid, how should I arrange the left and the right pointers? Notice in the first case, if the target is bigger, then this is all I have to look, right? I don't even care about this one. But what if the target is less than the mid? That means on this side. Yeah?
Right is mid minus 1.
Very good. Okay, so you're going to make right equals mid minus 1. Okay? Now there's only one other case. This says that the target is equal to A's of mid. In this case, we return true. Right? That means we found it, because that may turn out to be the target. Okay? So let's see, by using this algorithm, this is your binary search. This is binary search. Okay? Let's see how it's going to work. So we take the target 2, compare it to the mid. Right? Target is less than the mid. See that? Not the mid index, the mid value, right? So 2 is less than 8. What should I do to, which one I change now? Left or right? The right, right? Good. So I will change the right to what? Mid minus what? Right, so the right would become 1. Okay, right would become 1, and left, I'm not going to touch it. Left is still 0. Now with these two numbers, what is the new mid? The new mid is 0 plus 1. Mid is always computed using this formula, right? What's the new mid now? 1 over 2, that's 0. Okay, integer division. This gives you the mid index. So I should call this mid index so that you don't get confused. What is A of mid now? So that's the next compare element, right? So now at this point you say, oh, target is 2, A's of mid is 2, let's return true, right? So my algorithm at least on paper worked, okay? So let's do something that may not be so tricky. Okay, I'm going to erase this. Hopefully you took the numbers down for that target. I'm going to change the target for, I'm going to change the target to say something like 30. Okay, now the target is 30. I know target is not there, right? So I should somehow come up with a conclusion that target is not there. Okay? So my left, right, mid, all that stuff didn't change because I'm working with the same array, right? Okay, now the target is bigger than the mid, right? If target is bigger than mid, what do? We make the left be mid plus 1. Okay, so what happens to the left? It becomes 3, right? It becomes 3. And the right didn't change. Okay, right didn't change. What is the new mid now? 3 plus 5 over 2. Right? Left plus right over 2. That gives you 4. So the mid index is 4. What is the element at 4? 15. Alright? Alright, so let's do this again. So now we compare 30 to 15. Right? 30 is bigger than 15. That means we are back in this case here. The target is bigger than the new mid. Right? New mid element. So in this case I'm going to make, what do I change now? Left becomes what? Mid plus 1, right? So what is mid plus 1? 5. Because that's mid. Okay, left becomes that. And the right didn't change. All right. And then the mid, now if I compute mid, 5 plus 5 over 2 is 5. And what is A of 5? 45. Okay. Now I'm not done yet, right? Because now I look at target. Target is still bigger than the mid. Right? If target is bigger than mid, what do? I make the left the mid plus 1. So what does the left become? 6. Okay, this doesn't change. Now can I compute a mid now? There's something wrong now, right?
Yeah.
Because my left should be always less than or equal to the right. If the left is bigger than the right, that means you have an array of no size. That means there's nothing to search in. Okay, so that's your exit condition for the loop that you're going to be writing. Okay, the fact that the left becomes bigger than right indicates that the element doesn't exist. It's false. Okay? So that's binary search. It's not really difficult to record it unless you do recursion. Recursion is a little bit harder. But let's record the binary search here. Okay, so here's the binary search for an array of integers. I'm going to code what I just said on the board. Okay? So here's what I'm going to do. First of all, I'm going to check to make sure that I have an array to search. Okay, so you gave me an array. I will make sure that that array is more than size 0, right? What else I should test? What is the precondition for binary search?
Sorted.
Right? Sorted, right? Then I will search if it's not is sorted. Notice that I'm using the method I wrote before, right?
Oh, yeah.
So if it's not sorted, let's not bother to search anything because it's not going to be, you're not going to be able to find it, anyway, right? Even if it's there. You can return a meta message if you want, but if it's not sorted, then you don't search. All right. Otherwise, I'm ready to search. So I will define some things that I want to use. I will define a left, right, and a mid. Okay, those are the 3 variables I need, like in the board there. Okay, so let me call this min index or something so that you don't get confused with the. Yeah, min index is better, right? So I'm going to initialize the left to 0 and right to a dot length. Okay, mid index I'm not going to initialize it. If you want, you can initialize 0. That's fine. Okay, so I initialize that. And then I will have a loop. Okay, so whatever I did there, it's a while loop because it's not a for loop. Why? Why is it not a for loop? Like, why didn't I decide to use a for loop here?
We don't know how many times we're going to do
We don't know how many times you're going to go, right? It all depends on target, the array, all that stuff. So what is the condition under I should exit the loop? While the left, right, is less than or equal to the right. Okay, so I'm in business, right? As long as left and right, left is less than right, I got something to search. Right? I got some array to search. All right? So then I'm going to write some conditions. So I'm going to say, oh well, first of all I have to compute the mid, right? So what is the mid index? I said that the left, it's going to be the left plus right over 2. In fact, strictly speaking, you shouldn't write that because I think if you're doing maybe upper level programming, you might realize that if this left and the right are really large numbers, it could overflow. Okay, addition could overflow. And then there's a trick to write this as a minus. But let's not worry, let's assume that left and right are not that big. Okay, so it's not going to overflow the sum. In other words, if the left is like max int over 2 or something, that's going to be very bad. Okay? So let's do that, then I will do my comparisons. If A is a mid index, right, greater than target, what should I do? If A is of mid is greater than the target, then right gets mid minus 1. Right, else, if A is of mid index is less than the target, notice that I didn't have to, then the left, is of left index is less than the target, mid index is less than the target, then I'll make the left equals mid plus 1.
Yeah.
0, right equals mid minus 1.
Okay, else, what should I do otherwise? What is true if that's not true? What is true if that's not true? So this is not true, this is not true, then what's the other case? That means target must be equal to the A mid index, right? So this means that you should return true. That means you found it, right? Okay. Now Now, when do we return false? That means you
Wait.
didn't find it.
Yeah, professor.
Okay, so yeah.
Shouldn't it be right equals mid index minus 1 and left equals mid index plus 1?
Ah, yes. Yeah, I keep saying that.
That's it.
Okay, so now it's good, right?
Also, should right be initialized at a dot length or a dot length minus 1?
A dot length minus 1. There you go. Okay. So a lot of things you're catching, that's good, right? So you're paying attention to the key things here. This should be A dot length minus 1. In fact, you know, if you think it might be sort of cleaner, although not efficient, but it might be cleaner to just move this here. Okay, just define the mid index inside. It's not efficient, but gives you more clarity about the variables that we are dealing with, right? So left and right are initialized to the correct thing. And then as you go through this, right is moving to the left, and left is moving to the right. Right, at some point they're going to cross, or they're going to meet, and then we will decide, you know, at some point they're going to be the same, probably. And at that point, either that's going to be the target or it's not, right? You're going to cross over if it's not. This is it. This is your binary search. Right? Can you convert this to a recursive algorithm? Now, if you convert this to a recursive algorithm, this is not enough, right? Because you don't have loops. What else do you need here to make it recursive? Yeah?
Your bounds.
You bounds, that's right. So if you make it recursive, you also need to have bounds. Okay, left and the right are not inside anymore. Okay, then you're passing them into the function constantly by changing. So you can think about sort of making this a recursive call. Recursive call is not that different. You don't have a while loop. There are bounds on here, left and right. It says something like if a mid index is greater than target, binary search with the left the same, but the right is going to be mid index minus 1. They just change the arguments to it. When you start from 0 and then minus 1, and then kind of go from there. Okay? But that's okay. You can understand this. Okay, so that's that, and let's make sure that this is okay. All right. So let me show you how. Let's always testing the code is very important, right? So after I write the binary search, I will say, okay. So here, I'm going to use the binary search to search the array if it's sorted. In fact, I don't even have to do this here because I'm already doing it inside the binary search, right? Because I'm not going to search unless it's sorted. So this one says if it's sorted, let's just binary search for 2. What's the answer should be? False, right? Okay, so let's see whether it's going to be false. Okay, so the answer is false. Well, let's binary search for something let's do some test cases. Let's say 20, right? Oh, actually, why did it give me false? The array is not sorted, right? So it couldn't do the binary search. It's the wrong thing. Actually, you could do, yeah, so it gave me sorted from here because it says that it's not sorted. So now it's sorted, okay? So this should give you true, and this is going to say no, right? Because I'm binary searching for 20 in this array. 20 doesn't exist in the array. So I should get false, true and false. Okay? So let's try that. True and false, okay? But let's say that if you're doing good testing, then you always test for the edge cases. Let's test for 200, right? It's 200 there. So now it's true. Okay, so let's make sure that we catch the edge case. Okay, now it's true, right? And let's check for the edge case here, which is 4. right? So it should catch that. Still true, right? Let's check for something in between. Let's say, I don't know, maybe 50 or something, right? See if it catches 50. All right? And let's search for something that's completely out of bounds, like say -11 or something. Right? Obviously, that's not in the array. It can be in the array, but it's not. And now it's false. So when you search, you have to make sure that you're searching. You run the search algorithm. You carefully develop it, and then you test it. Right? That's what I'm doing here. I'm testing it before I submit it to AutoLab. I have to test it on my own, right? You guys are doing it because you have test or something now, right? You guys like test drives. So don't use AutoLab as a sort of a debugging tool. If you think about your own code, you can build good test cases, right? Like for example, I think when you're testing equals, right? What type of arrays you want to develop? What type of, obviously, you're testing. I know you know the algorithm for testing this, right? So, I think one of the challenges is that if you have a list and you have another list, and how do you know these two lists are the same? Right? Provided there could be null in between all that stuff, right? Okay, and you kind of know the algorithms. I guess I think the easiest thing to check whether two lists are the same, using what? If you sort both of them, right? They have to be identical, right? Element by element, right? But you don't know sorting, and I don't think you're supposed to use sorting for this assignment. So for this assignment, you're probably using some kind of a comparison thing to say, take something and see if it's here and so on, right? I think you can assume that things are not duplicated, because if they're duplicated, it's not going to work, right? If they're duplicated, it's not going to work. Your algorithm may not work. Okay? You can check the sizes, all that stuff, right? What was the context for that? I forgot why I got into this one. How did I get started here? What? Yeah, your project has these things, right? Correct. Yeah, that's what I think I was talking about. Yeah, sort of comparing two lists. They are strings, right? Yeah, 50 strings. Yeah, 50. Right. But not all 50 are filled. Right? So yeah, you can do any comparison as long as they're not null. Okay. So make sure before you compare two strings that they are not. One of them is not null. If it's null, then it's a problem. Okay? So because you could have null strings in the array. All right. So we talked about the linear search and the binary search. Okay. And binary search is a very really important search algorithm. The reason is that Okay, so let's talk about the complexity of search. And there are two search algorithms we know, linear search and binary search. All right, and we're going to talk about the best case, the average case, and the worst case. Okay? So when we talk about complexity, I think we mentioned that, I think prior to the Thanksgiving, complexity of search or anything, okay, complexity of algorithms, are discussed in terms of n. In terms of n is the number of elements that you have to process, number of elements. This n also can be the size of the array, a dot length, something like that, right? So that's the discussion. So if you're doing linear search, let's suppose that you're linearly searching, right? So let me also write the requirements on this side. Okay, for the linear search, do I need a sorted array?
No.
No.
No. Okay, so any array. If I have a sorted array, would that be helpful?
Depends.
Okay.
Depends on where you're targeting.
So suppose I have a sorted array, right? Like this, and I'm doing linear search. I'm looking for 4. Number 4. When do I stop? As soon as I hit 8, I stop. Right? Why would I bother searching beyond? Because I know anything else is more than 8. Right? So if it's sorted, linear search can be speed up. You know, you can speed up linear search. But if it's sorted, then you might as well use binary search, right? That's the best. For the binary search, you need to have a sorted array. Okay, so it's better here, any array but better sorted array. All right, now what is the best case linear search? How many things you have to touch before you decide whether it's there or not there?
1.
Best case is 1. Okay, I'm gonna write 1. We call that constant performance. The average case, you know, maybe somewhere in the middle, right? So the average case, we say that would be about n over 2. Maybe we have to look at maybe half the elements before we find it. In other words, if your array is completely random, and if the element is there, you're gonna find, if the element is there, actually this changes, right? If the element is there, half the time you will be able to find it. But if the element is not there, then you have to look at the whole thing, right? Because there's no probability guarantee anymore. Okay? So but let's assume that, you know, element is there. Right? The worst case is what?
N.
N. You have to look at the whole thing. Okay? Now let's think about binary search. That's a little bit tricky. Okay, in the binary search, okay, so the search space is size n. Remember the low and the high, right? It's 0 and n minus 1. Okay, and after doing one comparison, the search space becomes n over 2. Okay, after one comparison. After one comparison is you decide to go left or right based on where the target, you think the target might be. Okay? Now, after 2 comparisons, what will happen to this?
N over 4.
This becomes n over 4. Okay? N over 4. So you can see that this number is a power of 2. Next it will become n over 8. Right? So what will happen is it will become at some point some n over 2k. K is some number. I don't know what that k is, okay? N over 2k. But this number is going to be so big, it will be the same as that number. Right? So in other words, you know, at some, let me give you an example to get a sense of where I'm going with this. Okay, suppose your array size is 1,000,000. Okay, your array is 1,000,000 size. This is roughly 2 to the power 20. Okay? And after one comparison, this will become 2 to the 20 divided by 2. We know from algebra, this is 2 to the 20 minus 1. That's 2 to the 19. Right? And if you divide it again, it becomes 2 to the 18. Right? And you keep doing it until it gets to this. 2 to the 0. Well, what is 2 to the 0? It's 1. Right? So when you do binary search, you keep cutting the array in half and get to an array of size 1 eventually. And at that point, you're ready to make the decision, right? That's the worst that can be. Right? At that point, you say, okay, it's there or it's not there. Right? So, in other words, if you start with 2 to the 20, you have to do roughly what? How many comparisons? Roughly 21 comparisons here, right? 21 comparisons. Let me say 20 comparisons, okay? I will just ignore because the one I can ignore for large numbers, right? Now let's try to find out this relationship. If you take the log base of 2 to the power 2 to the 20, okay, how can I simplify this? You guys know, you should know this, right?
It's 20.
Okay, so you can take the exponent out, right? So this 20 times log base 2 to the 2. Well, log base 2 to the 2 is what? Is 1. Okay, so what it's telling you is this. This number is the number of things, n. Okay? The number of comparisons you have to do is approximately log base 2 to the n. Okay, that's what it says. All right? So that's why the binary search is going to be so fast. But the worst thing is that in the best case, and the average case, and the worst case, it's the same. Right? Best case, average case, worst case, it's the same. Because I won't be able to do it any faster. Okay? Do you get that idea, right? It doesn't matter. Because it's at the beginning or the middle. If it's the middle, you can say, okay, maybe I'll find it faster, right? But I think I'm gonna say they're all the same. Okay, you might disagree with me. I think I'm gonna be okay if you say the average. You cannot say average case is log base 2n, because I don't know what the array looks like. Right? The array could be really, screwed up array. I don't know. It's sorted, but it could be very weird. Okay, because of that, I cannot say anything about the best case, average case. I can only say it's log n. But the log n is not a bad number. Okay? In fact, I think the log, if you can get something to a log algorithm, that's the best. I think even if anyone knows the number of atoms in the universe? What's the number of atoms in the universe? Oh, do a Google search, come on. Number of atoms in the universe. Yeah? That's true. 10 to the 79?
Yes, 79.
Oh, 10 to the 79, okay. So the number of atoms in the universe is 10 to the 79. Okay, let's say 10 to the 79, okay? Well, what is this roughly as a power of 2? I'm going to use this fact. Right, so this is going to be 2 to the power 20. Well, this is going to be 10 to the 6 to what? How many 6s go into 79? About 11, 13? 13, right? But this is roughly 2 to the 20 to the 13. Because I have to replace this by 2 to the 20, right? So that's roughly 2 to the 20, that's about 260? 260, okay? So if you process all the atoms in the world in logarithmic performance, that's how many operations you need, right? If you take all the atoms in the world and sort it, okay, and search for some specific atom, this is how many operations you need to find it. So what is this equal to? 260. Right? So we can search, if you have binary search, to search all the atoms in the world, we can do it in less than 260 comparisons.
That's
So you
not
can see
bad.
why the logarithm is so important. All right? So it's a nice number. I think people love logarithms because logarithms are smaller than any power of n. Right? Take any power of n, like take n to the power 1 over p. P can be anything.
It's 10 plus 100
Okay? Any number. And this guy is still bigger than log. Okay? That n to the 1/2, n to the 1/3, n to the 100, so the 100th root of n is still bigger than log n. So this tells you the sort of the importance of algorithms. Okay. All right, guys. See you Wednesday. We'll talk about